Okay, everyone, I'm going to pick up where I left off at question 65 for the midterm. First it says, in the modern model of the atom, each atom is composed of 3 major subatomic or fundamental particles. 65 says, state the charge, that's going to be important, the charge associated with each type of subatomic particle contained in the nucleus. That's really important. They only want what's in the nucleus, not every subatomic particle. Because when we think of subatomic particles, we should think of protons, neutrons, and electrons. But what's in the nucleus? Only our protons and neutrons. So for 65, we want to say that a proton has a charge of, it's positive, or you could say positive 1, or just positive, and a neutron is neutral, or you could say 0, but only what's in the nucleus. Now 66 says, what is the net charge of the nucleus? Well, if you just told me that protons and neutrons are in the nucleus, protons are positive, neutrons are neutral or 0, okay, then I have to think that the net charge could only be my protons. So if they don't tell me exactly how many protons I have, what I want to say for 66 is it is positive. Positive. Or you could say positive the number of protons. For 67, we'll read the top. It says, John Dalton was an English chemist who proposed that the atoms were hard, indivisible spheres. In the modern model of the atom has a different internal structure. A, identify one experiment that led scientists to develop the modern model of the atom. Well, there's really only one experiment that we know a ton about as far as this class. You know, we had J.J. Thomson with his cathode ray tubes, but the main one is going to be the gold foil experiment. And that was done by Rutherford. You don't have to say Rutherford, you just had to say gold foil because that was the experiment, but that's the one I would choose if I were you because we know a lot of details. So if we describe this experiment, Rutherford shot alpha particles Now, alpha particles are positive. A lot of you said that he shot electrons, he shot rays, he shot lasers. Well, no, he just shot alpha particles. So I know we think of it kind of like a laser beam or a shot light, but it wasn't electrons. It's definitely important that we say positive. So you either need to say alpha particles or positive, but one of those has to be in there. So he shot alpha particles at gold foil. And really you could stop there. Some went through. Some bounced back. And from that, we got two different conclusions about the structure of the atom. C is going to ask about one of those conclusions for the internal structure. So I only have to say one of them. But based on this experiment, because some of them went through this part, we can either say, one, the atom is mostly empty space, or because some bounce back, they are positive. Two like charges repel each other. So two positives don't want to be near each other. That's why they would bounce back. He found a dense positive nucleus. For questions 68 and 69, I'm going to look at the information on this table. I can see they give me an isotopic notation. Oh, they're both copper. I'm going to notice that the 63 and 65 are their mass. Those are different. and I have my percent natural abundance and my atomic mass. This is a more specific mass than this is. 68 says state in terms of subatomic particles how an atom of Cu63 differs from an atom of Cu65. Well, we just said they had a different mass, but that is not subatomic particles. Remember, subatomic particles, I need to say protons, neutrons, or electrons. And what is different if my mass, my protons will not change. Copper will always, always, always have 29 protons because that is its atomic number. So what I want to do is say, well, if my mass is different, my atomic number isn't changing, it must be my neutrons. So Cu63 is a different number of neutrons. Again, if we said that it had a different mass, you're right, it does have a different mass, but again, in terms of subatomic particles, very important. 69 said show the correct numerical setup. So that means I don't have to solve it. That's important. For calculating the average atomic mass of the naturally occurring isotopes of cardamom. Well, that's a typo. It shouldn't be cardamom. You probably didn't notice on the test, but that should be copper because that's what's listed right there. So we're going to go on my average atomic mass. Now, if I notice that I have different percentages of those, this isn't a straight average. I have to do an average where I'm taking a weighted average. That means what I'm going to do, you're always going to take your mass and you're going to multiply it by your natural abundance. But you must move the natural abundance decimal point over twice or divide it by 100. So if you do that, you're going to get 62.930, always use the more specific atomic mass, times 0.6917. Now those two things are multiplied by each other. Now you're going to add those to now I have, I'm going to go on a different line, 64.928 times 0.3083. And I'm done. That's my answer. I'm multiplying my mass times my decimal abundance. I turn that percent into a decimal. It's important that you do it to the percent, not the mass, so you'll have it marked wrong. Okay, moving on. We are now up here at question 70. So let me read first. It says, a student used a balance in a graduated cylinder to collect the following data shown. Sample mass, 10.23 grams. Volume of water is 20.0. And volume of water and the sample is 21.5. 70. Calculate the density of the element. Show all work and report my answer to the correct number of significant figures. So we have two different points that are coming here. I'm actually going to do my work over here. So if I want the density is mass over volume. If I don't remember that, I can find that on my table T of my reference table. So I have that. Well, I have a mass. It's 10.23 grams. And I have a volume, but I should notice that I have two different volumes. Well, if this is the water and the sample, I want to get the volume of just the sample. So how do I do that? I have to subtract these. If I subtract, well, I don't want to do it like that, actually. Sorry, I'm going to subtract, but I want to do the bigger number minus the smaller. So I'm going to go 21.5 minus 20.0, and I get 1.5. I'm keeping with significant figure rules because when I add or subtract, I'm looking at the decimal places. Both of those have one decimal place. I have one decimal place in my answer. So I'm going to take this 1.5. This is the volume of just my sample alone. This is volume done by water displacement. You should remember you've been doing that for actually quite a long time in science. You did it in middle school, I'm sure, and I know that you did it in earth science as well. So I'm going to take that number, 1.5 milliliters, and I'm going to plug it in. And what I get when I plug it in my calculator is 6.82. And my units would be grams per milliliter. Now the problem is here's my work, there's my +1. But here, that is not my number of significant figures. If I look here, this is 1, 2, 3, 4 significant figures. There. Here, I have 1, 2 significant figures. So when I divide or multiply, I want to go by my least number of significant figures. That's this 2. So I have to round this. I can only keep the first 2. So the answer I want to report is 6.8 grams per milliliter to get both of my points. Now in 71, it said if the accepted value is 6.93 grams per milliliter, calculate the percent error. Remember, percent error is on the back of your reference table on table T, where you can get that equation. It is measured minus accepted over accepted. So they just told you this was accepted. So when I think about it, this must be my measured then. Well, really, this right here. I'm going to use my significant figures. So my percent error, my measured was 6.8. My accepted, 6.93. Divided by the accepted, 6.93. And I have to go times 100. And if I do that, let's see, here, I'll do it on my calculator. 6.8 minus 6.93 equals, divided by 6.93 equals, times 100. Now see how I get a negative number? When I'm doing percent error, I can always take the absolute value, meaning I can always make it positive. So I get 1.87590. I don't want all of these, so I'm going to round this, and I'm going to do significant figures here because of that. So I'm going to end up going 1.9. 1.9, unit being percent. Okay, now I go on to 72 through 74. I have this diagram. It says the diagram below represents 3 elements. They're all in group 13 and 3 elements in period 3, and their relative positions. So these would be the ones that are in period 3. This would be your group 13 because groups go up and down, periods go across. So it says some elements in the solid phase exist in different forms that vary their physical properties. For example, at room temperature, red phosphorus has a density of 2.16 grams per centimeters cubed, and white phosphorus has a density of 1.823 grams per centimeter cubed. So 72. Consider the period 3 elements in the diagram in order of increasing atomic number. We're looking at these. State the trend in electronegativity for these elements. Well, the trend for the electronegativity, I can always look up. Electronegativity, I can look up on table E. Nope, sorry, not table E, table S. So if I go to table S, let's go there. I'm going to do it for Al, Si, and P. Let's prove it to ourselves because we are doing a test, and that will be important. So I'm going to look. Let's first find Al. Al has an electronegativity of 1.6. Then I'm going to look at phosphorus, 2.2. And my last one, oops, sorry, I forgot Si, silicon, right here, 1.9. So 1.6, 1.9, 2.2, what's happening? It's increasing. And I can always look that up right in my reference table. So increasing is how I want to answer that. 73, compare the number of atoms per centimeter cubed in red phosphorus. Oh, my lights went off. Hold on. I hate these motion sensors. So, red phosphorus with the number of atoms in white phosphorus. Well, how the heck am I going to do this? Go back up and look at your densities. This is red density. This is white density. This is more dense. Well, density is how close the atoms are to each other, how many atoms that I'd have in there. So, bigger density, red has more atoms. Again, it's because that density is greater than that. Greater density, more atoms. 74. Identify one element from the diagram. Now that's important. Some people gave me answers that were not from the diagram. It said right here, from the diagram. That will combine with phosphorus. Okay, it's going to combine with phosphorus in the same ratio, okay, of atoms as a ratio in aluminum phosphide. Well, let's figure out. Aluminum phosphide, Al, look up its charge on your periodic table. It's +3. Phosphorus. If I look on my periodic table, I'm going to see phosphorus is -3. If I crisscross those, I just get, well, Al3P3, which we all know we simplify to AlP. So that means right here I have a 1-to-1 ratio. 1 Al for 1 P. So if I want that same thing to happen, I just have to pick somebody that's going to be in the same group. So up here we already said these were all in group 13. So you got two options. Both of these are right. So your answer here is going to be Ga or ion. Again, it's got to be one of those because they are in the same group. Now I move on once again. We're getting there, almost there. Here, let's read the top. Baking soda, NaHCO3, I might want that, can be commercially produced during a series of chemical reactions called the Solvay process. In this process, NH3 and NaCl and other chemicals are used to produce NaHCO3 and NH4Cl. Alright, they produce these. Maybe that's going to be important. Let's think about it. To reduce production costs, NH3 is converted from NH4Cl through a different series of reactions. This series of reactions can be summarized in the overall reaction represented here. It's unbalanced. So 75 says, write a chemical name for baking soda. Okay, well, let's find out who the heck was baking soda. Well, here. That's baking soda. So, I would say, okay, I know what Na is. Na is sodium. And most people got that. Now, here is where we go awry. This HCO3, this all sticks together. It's a polyatomic ion. Let me show you. You should always be going to table E and checking that these things, if they're polyatomic ions or not. I know you know CO3 is, but you're not going to always know them. So you have to check. So let's see. Well, I see, let's scan. I see carbonate, but I have more elements. Oh, look right here. HCO3. Hydrogen carbonate. You don't have to do anything to that name. You just take it. So you say sodium, hydrogen, carbonate. Easy peasy, but you have to remember, go to table E to look that up. 76. Baking soda would technically have both ionic and covalent bonding. Please explain why it would have both. Well, the things that have both ionic and covalent bonding, hopefully we went over that many, many times, would be anything that is polyatomic. And we already decided up here that hydrogen carbonate, right here, HCO3, that was on our table E. Remember, look right here. Hydrogen carbonate. So that's a polyatomic ion. It's going to have both ionic and covalent bonding. Remember, HCO3 is all nonmetals, which gives it the covalent, and ionic because I have a charge, an overall charge. All right, 77 through 79. Let's read the top in case we need it. Rubbing alcohol is a product available at most pharmacies and supermarkets. One rubbing alcohol solution contains 2 propanol and water. The boiling point of true propanol is 82.3 degrees Celsius at standard pressure. All right, maybe I need it, maybe I don't. 77, explain. In terms of electronegativity differences. In terms of electronegativity differences. Really important. We got to start drawing our eyes to that. Why? A CO bond is more polar than a CH bond. Well, I know you know how to look up the electronegativity values. I know you know if it goes between 0 and 0.4, it's nonpolar. If it goes between 0.5 and 1.6, it would be polar. But they're talking about the electronegativity difference. So if you actually figure this out, I need you to compare both of them. Easier would be anytime it says in terms of that, well, it either has a larger electronegativity difference or a smaller one. That's always the answer. So CO, if I look up the electronegativities, again, I'm going to go to my table S. Let's go here, I'll show you. They're both carbon. So carbon is 2.6. Let's look up H, 2.2. Oxygen, 3.4. So if I look, this is 3.4. This is 3.2, 2.2. Oh, no, I just lied. 2.6, sorry. 2.6, let's see, 2.6. Well, I don't even need to do the math. I can see that when I subtract these and I subtract these, this is going to be a bigger number. So in terms of electronegativity differences, CO has a larger electronegativity difference. Also important, say electronegativity difference. If you just say electronegativity, you're not telling me that you know to subtract those and get the difference. So difference is the key. 78, identify a strong intermolecular force. Okay, strong intermolecular force of attraction between an alcohol molecule and a water molecule. Identify. Name it. Well, you know types of intermolecular forces. First, it mentions water. That'd be my key. I'd probably go off of that and say water is always going to have hydrogen bonding. Remember, hydrogen bonding is when H is with N, O, or F. So hydrogen bonding, and I could also go with another answer I would accept is dipole-dipole. Because water is polar, and if they're talking about a solution, 2-propanol must be polar too if they're going to go together. Remember I told you how like dissolves like, so polar likes to be in polar. We'll talk about that more as we move on. So less people said this, but that was an acceptable answer. This is the one most people said they got it correct. And again, water, hydrogen bonding. 79. Explain in terms of charge distribution. Ooh, getting a little crazy on you. In terms of charge distribution, Y molecule of 2-propanol is a polar molecule. Remember, when I start talking about polarity in a molecule, I'm talking about shape. So when they say in terms of charge distribution, you could say it back just like that. So it's either going to be even or uneven. If I'm polar, I have an uneven charge distribution. Or I'd allow you to say that if you have an uneven charge distribution, what you're actually saying about the shape is that it is asymmetrical. A lot of you thought too hard on that one. That's it. Saying uneven charge distribution when it's polar. That would make it asymmetrical. All right, almost there. 2 more questions. All right, let's read this top. 80 and 81 go here. Silver-plated utensils were popular before stainless steel became widely used, making eating utensils. Silver tarnishes when it comes in contact with hydrogen sulfide, H2S, which is found in the air and in some foods. However, stainless steel does not tarnish when it comes in contact with hydrogen sulfide. Okay. In the space in your answer booklet, draw a Lewis dot diagram for this compound that tarnishes silver. All right, well, they told us somebody tarnishes silver. Stainless steel does not tarnish when it comes in with hydrogen sulfide, but it said silver tarnishes. Okay, I'm right here. Silver tarnishes when it comes into contact with hydrogen sulfide, H2S. They want me to draw H2S. So, I need a little more room. I'm going to go down here. So, H2S, I would say, is that ionic or covalent? 2 nonmetals, it's covalent. That's always what I should decide. So, I'm going to share my electrons. So, I'm going to figure out how many I have. Hydrogen has 1 valence electrons, but there are 2 hydrogens. Plus sulfur is going to have 6 valence electrons. Remember, I should probably make sure you remember. I want valence electrons. I go here. And I go to that very last number in the electron configuration. So sulfur has 6. That's going to give me a total of 8 electrons. So I got to decide who's in the middle. Well, there's only one S. So, put S in the middle. I gotta at least have single bonds. I always start there. When I did a line, that's 2 electrons. So I use 2 electrons, 4 electrons out of 8. So I've got 4 left. If I've got 4 left over hydrogen, no, don't give them to hydrogen. Hydrogen doesn't want any more, it only wants 2. But this S, and pretty much everybody else on the periodic table, this wants 8. So it's got 4, give it 2 more. Now it's got 6, give it 2 more. Now it has 8. Recheck. Do I have 8? 2, 4, 6, 8. I used all of my electrons. H is happy. S is happy. I'm good. Now you could leave it like this. Technically, it would be drawn bent just like water is because I have extra electrons on my central atom. I don't care which way you draw it. Most of you drew it like this. That's fine. Water, I always want you to bend. This would be just like water. All right, so then 81, last question. In the ground state, an atom of which noble gas, okay, they're talking about noble gas, which noble gas has the same electron configuration, all right, that might be important, as the sulfide ion in Ag2S? Well, let's look at the sulfide ion. Well, S, again, go back here. Top oxidation number, -2. Sulfide ion is going to take on -2. I'm going to look at its irregular electron configuration for S, 286. So normally it's 286, but this 2 means I'm going to add 2. So I'm adding 2. So really I'm going to get 288. So S minus 2 has that configuration. All I have to do is figure out which noble gas has the same one. I'm going right here. Oh, look right there. 288. Argon. Argon is my answer for 81. All right, happy correcting.